Hello guys, in this video we are going to learn about elements of dynamic programming. Dynamic programming is an optimization approach. Let us see how similar or different is this approach from the other optimization approaches that we have seen earlier. In linear programming, nonlinear programming, mixed integer programming and mixed integer nonlinear programming, the basic idea is that you create a mathematical model and you use a corresponding solution method to solve that mathematical model. Whereas in dynamic programming, you do not need any mathematical model. However, you need to understand the elements of dynamic programming, and then you use a recursive method to solve the dynamic programming problem. Now let us see when we can use this dynamic programming or the recursive approach. When you have an OR problem, and you realize that this problem can be broken down as a sequence of interrelated decision-making problems, then you can use dynamic programming. This sequence of interrelated problems should have a unique structure. Now, what is that structure? The very first problem in the sequence should be very easy to solve. And given the optimal solution of the very first problem, the next subproblem should be easy to solve. Not only that, but the optimal decision at the second subproblem should be independent of the decisions that you made in the first subproblem. And this is called as principle of optimality. Now continuing with this recursive method, now you have the solution of the first two problems, and then you solve the third problem. And given the solution up to the third problem, you solve the fourth problem. Similarly, you continue until you solve the overall optimization problem. And this is dynamic programming approach. Now how to use this approach? Well, we need to identify these three elements. That is nothing but the stages, the states and the decision. Stages are nothing but those subproblems, and every stage has a stage variable. The possible values of those stage variables are nothing but the states. Now in a dynamic programming problem, the decision that you make will be at a given state, and from that state the decision will take you to the immediate next stage to a particular state. And that is how the stages, the states and decisions are defined in general. To understand better, let us take some examples and see how these three can be defined. Let us take the shortest path problem. You are given with bunch of cities. You have an origin city and destination city, and you like to start from origin and reach the destination. At the origin city, you have three decisions to make, either to go to city 1, city number 2 or city number 3. And from city number 1, you have two decisions to make, so on and so forth. You make the decisions and you reach the destination. The goal is to find sequence of decisions such that you reach from origin to destination through the shortest path. Now for this shortest path problem, you can identify that the stages are nothing but these cities. Notice that the decisions are taking you from a state in a stage to the next stage in a state, and these decisions are highlighted by the green arrows. Let us see how these three elements can be defined for workforce size planning problem. Now in this workforce size planning problem, the idea is that you have a contractor or a manager who has a plan for the next 6 months, and based on his plan, he estimated that he needs so many employees in every month. For example, here in month number 1, contractor needs 10 employees. In the month number 2, 15 employees, so on and so forth up to the 6th month. Now the contractor knows that the maximum number of employees that he needs is 15 and the minimum is 9. However, he is not sure how many employees or how many workforce to have during each of these months. He cannot have less than the minimum number of workers. For instance, in the month 1, he cannot have less than 10. And in the month number 2, he cannot have less than 15. On the other hand, he can have more than minimum requirement. For example, in month 1, he can have 11 employees or 12 or beyond. Now, if we have more than needed, if we have excess employees, then some of them will be idle and he is going to pay for them for nothing. Whereas if we hire or fire an employee, he has to pay some cost. For hiring, he must do some advertisement, some interviews, and there will be a cost for that. For firing, there will be also a cost of goodwill. So the cost of this contractor is to find the right workforce size for each month, such that the overall cost of hiring, firing, maintaining the workforce is minimized. In this problem, the stages could be these months, and whenever you have a problem with time periods, the time periods can be considered as stages. The stage variable is number of employees. For example, in month 1, the number of employees could be 10, 11, 12, up to 15. Whereas in month 2, the number of employees could be only 15. And so on and so forth. So these are the states for the stages. Now the decision that you make at the beginning of every month will change the number of workers. For example, all these are the possible decisions that you make. For instance, here you have at the beginning 11 employees, and then you made a decision to hire 4 guys, and now it becomes 15 employees. And from here you have 15 employees, you make a decision to fire 1 guy, and you have 14 employees. So on and so forth, you have the entire decision tree. Now the final example is knapsack problem. Knapsack problem is one of the classical OR problems. The idea is very simple. Let us say you are planning on a vacation trip and you have a knapsack to pack, and in this knapsack you are planning to pack some items. For every item that you pack, it will consume some space in the knapsack. However, for every item there is also some significance or worth. The objective here is to pack as many items as possible that has the total highest or maximum worth. This problem can be written mathematically as follows. You are trying to maximize the total worth subjected to the space constraint. Here the variables y1, y2, y3, y4, they represent the number of items that you pack. For example, y1 represents the number of items of type 1 that you pack. Y2 represent the number of items of type 2 that you pack, so on and so forth. And W1, W2 represent the corresponding worth of those items. S1, S2 up to S4, they represent the space that is required for each item. And that's the optimization problem. Whenever you have an OR problem with a single inequality constraint, you could convert it like this, where variable R represents the remaining capacity. Now, in knapsack problem, every item corresponds to a stage, and the remaining capacity in the knapsack corresponds to the states. And whenever you make a decision, you move from one state to another state. For example, you can see that these are the possible states in the stages. For instance, if you have 0 items of type 4, then the remaining capacity is 6. If you place 1 item of type 4, then the remaining capacity is 4. If you place 2 items of type 4, remaining capacity is 2. And these are the possible decisions that you can make for the dynamic programming problem. To summarize, we have seen the differences and similarities of dynamic programming with the other optimization methods. We have also seen what are the elements of dynamic programming. Then we have identified the elements of dynamic programming problem in the shortest path problem, workforce size planning problem, and the knapsack problem. That's it. That's all, folks.